Hello class, welcome to lesson 5.3 in geometry. So we're going to talk about medians and altitudes of triangles. So our questions for this lesson is going to be about the properties of medians in a triangle and altitudes. So what are those properties as they relate to medians and altitudes for triangles? And our goal is to be able to find the points of concurrency for medians and altitudes. So our vocab for today includes altitude, centroid, median, and orthocenter. So remember in the previous lesson, 5.2, we discussed two special segments of triangles. We discussed perpendicular bisectors and angle bisectors. In this lesson, we're discussing altitudes, and we'll discuss another one as well, the median. So let's talk about an altitude. An altitude is a perpendicular segment from a vertex of a triangle to a line containing the side that is opposite the vertex. Remember that the vertex is the corner of the triangle, the corner point. So if we're going from, say, D, let's say we're interested in side DC. So we're going to extend side DC. Our vertex in this example that we're interested in is A. So we want to find the altitude going from the vertex A to the opposite side, CD. And so we're going to extend CD. And that right there is my altitude. So again, the vertex here is A, the opposite side is CD. But the only way that I can get a right angle is if I extend CD over so that I can get a right angle down here. Similarly, we can also do an altitude for vertex D. The side opposite of D is AC, this side right here. And if I want to draw an altitude, I need to draw a line that crosses that at a right angle, and that would be my altitude for that vertex. So I can do this for multiple vertices for this triangle. Now let's look at a median. So a median of a triangle is a segment that has an endpoint at a vertex and extends to the midpoint of the side opposite the vertex. So you start at a vertex, a corner point of a triangle, and you extend it, and you basically cut the other side in half, but you're doing it at any angle. Basically you're extending it, and it doesn't have to be at a right angle or anything like that. It just has to touch the midpoint of the opposite side. So for example, if we wanted to go from D to the opposite side is AC, well then the midpoint of AC is over here. It's the point that cuts this in half. So the median of a triangle basically cuts the opposite side in half. So the median bisects the side opposite the vertex. And so for altitudes, depending on the triangle that you have, you can actually get altitudes that are outside the triangle. Like in this case, in the first case for the obtuse triangle, the altitude is actually outside the triangle. For an acute triangle, notice that the altitude is can be drawn inside the triangle if we're talking about the vertex A. For a right triangle, if you're talking about the vertex A, then it turns out that the altitude is right on top of that right triangle. So basically this side is the altitude itself. Now, of course, if you're talking about an altitude like D, well then that's going to be something like this at a right angle. Same thing here. It's going to be something like this at a right angle. And then here, it'll be something like this at a right angle. So the altitude changes if you're talking about a different vertex, but you get the idea. If we're talking about vertex A, then in this case, vertex A is going to be on the right triangle if we're talking about that altitude from A to D. All right, so altitudes can change. Now, let's talk about the medians first. So we're going to construct the median, and then we're going to identify the point of concurrency for the medians, and then we're going to discuss the theorem for the medians. So let's go ahead and construct the median. So if I want to construct the median, I'm going to take my compass, I'm going to draw an arc above and below at 2 points, and then I'm going to mark the middle between those 2 points. And I'm going to do that for all of the sides here. And all I want to do is just mark the middle of each of those endpoints by constructing arcs. And then I can go ahead and connect the corners of the triangles to each of those midpoints. And therefore, the point of concurrency is going to be where those three medians cross. So this point of concurrency has a special name, which we'll get to. So let's go ahead and enlarge that diagram. So this point G right here that you see here, where all three lines cross, all three medians cross, has a special name, and it's known as the centroid. The centroid is the point of concurrency of the medians of a triangle. Now the centroid, so right here, this is a median. AD is going to be one of our medians, right? And so the centroid, notice, is not halfway through the median. So if we look at median AD, this is the halfway point of median AD. Notice that the centroid is not actually in the middle of AD. It's actually a little bit to the right of the middle. It's actually 2/3 of the way into the length AD. So if we were to cut AD into 3 pieces, 1, 2, and 3, notice that the centroid is located in the second piece out of the 3. And so it is located 2/3 of the way from A to D. So the centroid is not located halfway, it's located 2/3 of the way. Turns out you can do this for each of the midpoints. And it's always going to be located 2/3 of the way from each vertex along the median. So for example, if we look at this if we look at this median right here, EC, well, the vertex is C. And so I know if I cut this into 3 pieces, 1, 2, and then 3, this is 1 piece, 2 piece, 3 piece, then it's 2/3 of the way from the vertex in this case being C. And it's 1/3 away from the side. So it's always 2/3 of the way from the vertex. Same thing here. If I look at this one, the vertex is B. And so it's 2/3 of the way from B to F. All right, so let's look at the concurrency of medians theorem, which uses this fact that we mentioned with the 2/3. So the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay, so basically, if you're constructing medians, then they're concurrent at a point, and that point is known as the centroid. But also, that centroid is located in such a way that it is 2/3 of the way from each 2/3 of the distance for each median from the vertex. Okay, so this is my vertex. This is going to be 2/3 of the way. So basically, if I want to get if I know the distance AD, let's say the distance AD is 5, or let's say it's 6. Then to get AG, well, that's going to be 2/3 of the way, right? So I got to do 2/3 of 6. So if this whole thing is 6, for example, well, then I got to do 2/3 of 6, right? To get this little chunk right here. So that's what this says here. To get AG, I need to do 2/3 of whatever the total is. And if the total is 6, then I got to do 2/3 of 6. So if I want to multiply these two fractions, remember, put this over 1, multiply straight across. 2 times 6 is 12. 3 times 1 is 3. 12 divided by 3 is 4. Now, if I go ahead and actually do this, well, if I know that this whole thing is 6, well, then I know that this little chunk here is 4. 4 is 2/3 of 6. And therefore, this has to be 2. So you see how this can be useful, because you can do calculations to get how long each of the sides are for the median. And this works for all the medians here. All right, so let's look at an example. So we have here a centroid. We know that part A is a centroid because we got something going from the vertex to the midpoint. This is the midpoint because it's cutting this in half. Same thing here. This is a midpoint because it's cutting that in half. This is a midpoint because it's cutting that in half. All right, so therefore this must be a centroid. And so therefore it follows that 2/3 property. So if we want to figure out Jn, so we want to figure out how long that line segment is. Okay, so we know that 2/3 of that total, Jn, whatever Jn is, let's say Jn is 20 or something like that, I know that 2/3 of Jn is going to give me JQ, because using that 2/3 rule, right? So, but we know that JQ is 18. And so therefore 2/3 of Jn has to be equal to JQ. All right, and so now, but we know what JQ is, right? So we got 2/3 times Jn is equal to JQ, but JQ is equal to 18. So 2/3 of the total is 18, and I can solve this equation. Just think of this as a variable, all right? Just think of that as nothing more than a variable, like x, for example. All right, so we want to solve for Jn. So we're going to multiply both sides by the reciprocal. Remember that if you have a fraction here, you want to multiply by the reciprocal to cancel it out. You see 3 divided by 3 here cancel, and then 2 divided by 2 cancel. And then do the same thing on the other side. Again, put this over 1. So we have Jn, again, multiply straight across, or you can use the shortcut, 18 divided by 2, which is 9, and then 9 times 3 is 27. Okay, so either way works, it doesn't really matter. Let's go ahead and multiply straight across as well. So 18 times 3 is 54, 1 times 2 is 2, and then 54 divided by 2 is 27. Now that other trick that I was showing you was the trick that I can do 18 divided by 2, and that would be 9. And then 9 times 3 is 27. Either way, I get the same answer. So if I did this, I would get 9 times 3. So a couple ways, different ways that you can solve this. Either way, Jn is equal to 27. For part A. Now for part B, we know we're looking for AD, which means we're looking for this total. Now we know that this part from the vertex to the centroid is always going to be 2/3, which means the distance from the centroid to the other side, the midpoint here, is always going to be 1/3. And so we know that 12 has to be 1/3 of the total, okay? So we know that the total is AD. And I know if I did 1/3 of the total, 1/3 of AD, which is, this part right here, this little chunk. So 1/3 of AD is gonna give me 12, because that's what it's equal to. It's equal to 12, and that's 1/3. All right, so then we're gonna solve this equation. So we're gonna multiply by the reciprocal, 3 over 1 on both sides. 3 over 1 is the same thing as 3 though, so it doesn't really do anything on the right side. But it cancels out here and on the left side, and we got AD. And 12 times 3 is 36. We can ignore that 1 on the bottom. So this has to be 36. Okay, and that's how you do calculations with centroids. All right, so what's the significance of the centroid? Now the centroid, the significance of it has an actual physical significance. And so if you're interested in taking this triangle on the right and actually balancing it, thinking of it as a physical object. If I wanted to balance this physical object, this triangle, then I would need to place my finger or some kind of post or something, some kind of object that I would want to balance this on. Where would I place this object? Well, I would place this object somewhere on the centroid of that triangle. And if I do so, it'll balance that triangle perfectly without any external forces. And so you can imagine this is something that is more science related or physics related or engineering related, where you want to figure out the centroid of an object so that you can balance it out and with no external forces. So if I wanted to balance this object, I would have to balance it on the centroid. And so I would need to calculate this. I would need to calculate where the centroid is located. Of course, I can do that using medians, like I showed you with the triangle earlier. And so the centroid is actually a spot where the center of gravity is located. So the center of gravity, which is where you would have to balance this triangle, would be located at the centroid. So locating special points like the centroid is important in fields such as physics and engineering. You'll be, in engineering or physics, you're usually dealing with tons of objects, including triangles, like triangular objects. And so you have to calculate the centroid, the center of mass or center of gravity, when you're dealing with forces on that object. So although the center of gravity can lie outside of certain objects, we, for the purposes of this lesson and, for geometry, when we're talking about triangles, The centroid is only on the inside of the triangles, okay? So it's always going to be on the inside. It's not going to be on the outside or anything like that. Like, for example, the circumcenter that we talked about last lesson. In the last lesson, the circumcenter could be located on the outside or on the top, or on top of the triangle itself. But for the centroid, it's going to be located on the inside. All right, so now let's switch over to altitudes. We want to construct the altitude, and we're going to construct it 3 of them, and then figure out where they intersect. So we're going to take our compass. We're going to extend it out from A, or let's go ahead and draw an arc from A to the side BC. And notice that it crosses it almost about twice. And so we want it to cross twice, so we're going to extend BC just so that it crosses it twice. And then draw an arc at the points where they cross the arc for A, BC. And then we can connect those, and that will be our altitude. Let's repeat that for the other side. We're going to draw an arc through AC, and it crosses it at 2 points, and then draw an arc from each of those points, and then where they cross, you're going to connect those. Let's repeat that for the other side. We're going to go from C to AB. We're going to draw an arc, and looks like it doesn't touch at 2 points, so we're going to extend it so that it crosses it at 2 points, and then we're going to draw arcs from those points that they cross, and then connect those with a straight edge. And then, so even though that animation was quick, I would urge you to rewind it if you need to see it. But that's how you would construct the 3 altitudes for this particular triangle. Now, and for this particular triangle, since it's an acute triangle, it's actually located on the inside. So where they cross is actually located on the inside. So that's point P, the point of concurrency for altitudes. Now, it has a special name. This point of concurrency for altitudes does have a special name, and it's known as the orthocenter. So this is the point of concurrency for the lines containing the altitudes of a triangle. So if you were to do all the altitudes, they'll cross at a certain point, and that point is called the orthocenter. Now, like we're going to get into in a little bit, it doesn't have to be located on the inside. It could be located on other points on different triangles. So like I said earlier, the orthocenter can be located outside the object itself. All right, so kind of like the circumcenter. So the only ones that are only located on the inside are the centroid, which is the one that we talked about before, and the incenter. So those are the 2 that are inside the triangle. Orthocenter and circumcenter do not have to be inside the triangle. So for obtuse, it lies on the outside. Acute triangles lies on the inside. In right triangles, it lies on top of the triangle, so on the triangle. In this case, for this right triangle, it's located on the vertex. So basically, if I were to do, remember, so we're looking at altitude. So from here to here will be a right angle. And then if I'm going here, well, I need to go at a right angle, right? So I have to go down here. That's a right angle. And if I'm looking at this vertex, well, I need to do a right angle on the opposite side. Well, if I do this, that's a right angle. And so therefore, they all meet at this point. If you were to have all these altitudes, so they all meet at that point. And therefore, they're on the vertex. All right, so let's discuss the concurrency of altitudes theorem. So the lines that contain the altitudes of a triangle are concurrent. So that is the theorem. There's really no other special properties per se, other than the fact that it's a right angle and they're concurrent. Okay, so the only real importance of the altitudes is that if you draw all 3 of them, they'll be concurrent just like the other measures of center, or just like the other triangle centers that we discussed, rather. Okay, so in this case, if we have 3 altitudes drawn, they will cross at a singular point, called the point of concurrency, in this case, the orthocenter. In that case, KQ, LN, and MP are concurrent, and that's simply the theorem. Now, let's go ahead and show you I'm going to go ahead and show you a way to remember each of the centers. So, and I'll do that in this slide here. So if you would like to remember which special segment corresponds to which triangle center, then I would suggest looking at this acronym, or this mnemonic rather. So for example, we know that altitudes can cross at a point called the orthocenter. How can we remember that? How can we remember that a median crosses at a centroid? So let's use this mnemonic to help us out. So we have my cousin owes Anna banana ice cream, probably before Christmas. There's other mnemonics to help you remember, but this is one of those mnemonics. So for example, my cousin, that stands for median and centroid. So medians that cross lead to a centroid. And here we have O and A. Oops, I forgot. Let's see. I forgot another word here. Always. So my cousin always owes Anna banana ice cream, probably before Christmas. So yeah, there should be another A word there. So A and O. So A stands for altitude, and O's, that stands for orthocenter. So altitudes lead to orthocenters, just like this example right here. And Anna banana stands for angle bisector. Ice cream, IC, stands for incenter. So incenters are the result of angle bisectors crossing. And probably before, PB stands for perpendicular bisector, and then C stands for circumcenter. Okay, so this is a nice little mnemonic to help you remember. There's other mnemonics to help you, but this is one of those examples. Hopefully that helps you to remember the different centers. All right, so let's look at an example with that. Let's look at construct a triangle here. Basically, what they do give us in this problem, they give us 3 coordinates, and we're just plotting those coordinates. So what I just did is I took those coordinates and I plotted them on graph paper, okay? So 0, 0's here, we have 3, 12, and we have 10, 5. So the first thing you want to do if they give you coordinates is to draw the triangle using those coordinates, as I did here. Now, if you want to find the orthocenter of a triangle, we're going to actually find the equation of the orthocenter. We're going to actually find the actual location of the orthocenter. And to do that, we have to come up with equations of lines. And so we're going to be doing a bunch of calculations as they relate to lines. Okay, so first draw the triangle like we did. Next, what we want to do is we want to figure out the slope of this line LM. Remember that slope is calculated by using rise over run. And so to calculate the slope of ML, I'm going to do rise over run. So the rise here is, or in this case, we're going down, right? 1, 2, 3, 4, 5, 6, 7. So that's a -7. You can also do it by subtracting 5 and 12. So 5 minus 12 is -7. And that's going to be my quote-unquote rise. And then to get my run, I can count the number of units, of course, or I can simply subtract the x coordinates, 10 minus 3. And that'll give me 7. All right. And so rise over run is going to be -7 divided by 7, which is going to be -1. So my slope for this line is -1. Again, I need that slope because I need the equation of line ML. And so I want to be able to draw a line that is perpendicular to LM, right? Or ML. And so if I need that line to be perpendicular, well, then I need to figure out the perpendicular slope. So this line that I just drew and dashed is the altitude, or it's the altitude for this triangle, one of the altitudes for this triangle. And notice it has to be at a right angle. And so to get the perpendicular slope, remember, put this over an invisible 1, and then you're going to flip that fraction and then change the sign. Every time you want to find the perpendicular slope, you flip the fraction, change the sign. And so if you did that, you're going to get positive 1. All right, so now we know that the slope of this dotted line right here is positive 1 rather. Okay, so now we're going to figure out the equation of that line using y equals mx plus b. So we need to pick a point on that line. So let's pick 0, 0, because that's an easy point to deal with, right? That's a point on this line, technically. All right, so let's pick 0, 0 as one of our points, and we know that the slope has to be 1, so we're going to be using that as well. So we're going to plug in 0, 0 for x and y. So y is 0, x is 0. And now we know that, remember, that m is 1. So we plug that in, 1 times 0 plus b. 1 times 0 is 0. So we get 0 equals 0 plus b. That means b has to be equal to 0. We're going to plug that into that equation. And so we get y equals 1x plus 0. And so our equation is y equals x. And so we go in ahead and labeled it. So now we got y equals x for that line. All right, so let's go ahead and look at another altitude. Basically, we want two altitudes. We want to figure out where those two altitudes cross. Where they cross is going to tell us where the orthocenter is, because remember, the orthocenter is when the altitudes cross, right? So we need to figure out the equation of another altitude. So let's go ahead and look at the slope of OM in this example, or KM rather. So if we want to figure out the slope of KM, we need to do another rise over run. That's given in blue here. So the rise is 12. You go up 12 units, or you could do 12 minus 0. And the run here is 3 minus 0, which is 3. And so 12 divided by 3 is 4. So the slope is 4. Let's go ahead and draw the altitude. So there's my altitude from L to the line segment MK or KM. I want to figure out the slope of that blue dashed line. In order to do that, I need to do the little trick that I showed you for the perpendicular slope. So put this slope that we just calculated over an invisible 1, and then you're going to flip it and then change the sign. So if you flip it, you get 1 over 4, and then change the sign to make it negative. So it's negative 1 over 4. So now we know the slope of the blue dotted line. All right, so now we're going to use y equals mx plus b. We want to figure out the equation. Of course, we're going to plug in the m that we just found out there. But we need a point on that line. So we're going to choose the line 10, 5. The point 10, 5, because that's the only point that we know on the line. So we're going to plug those in to the equation. And we get 5 for y, and 10 is x. And remember that m is negative 1/4. So we plug those in. We get 5 equals, remember to multiply this fraction with this number, you just do 10 times 1, and then this has an invisible 1 there. So 1 times 4 is 4. And so that's how we get 10 over 4. Now we're going to solve this equation. So we're going to solve for b. So we're going to reduce the 10 over 4 into 5 over 2. Okay, so the way we did that, we just reduced it by 2, divided by 2 top and bottom. Now we're going to add, we're going to convert the 5 to 5 over 1, and then we're going to add the 5 over 2 on both sides. So let's convert the 5 to 5 over 1. We need that to be a common denominator. So when you add two fractions, you need to have the same denominator. So we're going to multiply the top and bottom by 2, and that becomes 10 over 2. Now we're going to add the 5 over 2 to both sides. 5 over 2 plus 10 over 2 is 15 over 2. So b is 15 over 2. And so now we're going to go ahead and plug 15 over 2 into the equation right here. And so then we get negative 1/4 x plus 15 over 2. Again, we know that m is negative 1/4 because it's right there. So now we got the equation. Let's label that on that line. Okay, so now we got both equations. Y equals x, y equals negative 1/4 x plus 15 over 2. So now what do we do? Now, because we want to figure out where they cross right here, we want to figure out where they cross algebraically means we have to set the two equations equal to each other. So the orthocenter is where both those blue and the black lines intersect. And so where they intersect is where they're equal to each other. And therefore, we're going to set the two lines equal to each other. So we got y equals x has to equal to y equals negative 1/4 x plus 15 over 2. So we're simply setting the x equal to that because we're replacing y with x. So basically y is no more, you're replacing it with x. And so that's your new equation, x equals the blue. Now we're going to solve that. So we're going to move the 1/4 x to the other side by adding it. But before we do that, we have to convert this 1 in front of the x into a fraction, 1 over 1. Remember, we need a common denominator, so let's multiply by 4 top and bottom so that they both have the same denominator of 4. Now we can go ahead and add the 1/4 x on both sides, and we get 4 over 4 plus 1 over 4 is 5 over 4. So we get 5 over 4x equals 15 over 2. We're just bringing this down. And of course, these cancel. And then we want to solve for x, so we're going to multiply by the reciprocal, 4 over 5 on both sides. Remember that you want to flip this, and that'll be reciprocal, so that's how we got 4 over 5. You always want to multiply by the flip of the fraction, and so now these cancel. And then multiply straight across. 15 times 4 is 60, 2 times 5 is 10, 60 divided by 10 is 6. So now we know where these two lines cross. They cross at x equals 6, which makes sense from our graph if you think about it right here. So that actually does make sense. So that x coordinate is 6. Now let's find the y coordinate. Since we know x is 6, we can go ahead and plug that in. Y is equal to x, right? And so if y is equal to x and x is 6, then y is equal to 6. So the coordinates here are 6, 6 from the orthocenter. Now, could you have determined it by approximating? Of course you could have. You could have drawn an approximate altitude for both of them and then figure out where they crossed. That would be one method. However, if you wanted to do it algebraically, this is how you would do it algebraically. And so the final coordinates are 6, 6 for the orthocenter. All right, that'll do it for the video, guys. I hope you learned something from this. And as usual, I'll see you in the next one.